So let's take a look at some of the solutions to the sequence of coding that I asked you to look at the other day. So all of these, just to remind you, all of these are going to start with the exact same setup of cards, right, just for example. And that every time we start a new section of code, let's assume that your left hand is on 0 and that your right hand is on card number 1. Okay? So I'm going to try to trace this as best I can, maybe with the pen, just to see if we can keep track of where we ultimately wind up. So the first command says shift the right hand to the right. Remember that the shift command will just move it one position in whatever direction it was told to do. So now the right hand is on 2. Next, shift, so that's item number 1. Item number 2, shift the right hand to the right. And we'll shift the right hand to the right. And item number 4 says shift the right hand to the right. And item number 5 says shift the right hand to the right. And item number 6 says shift the right hand to the right. And then stop. So ultimately, what does this program do? This program moves the right hand to the right 6 places. Right? And ultimately, the left hand remains on 0, and the right hand goes all the way to the end to card number 7. Okay, so very straightforward. Here's a really good example of just we kind of threw this concept out there the other day called top-down programming. The computer will always want to start at the first line of commands and then just work its way as best it can down to the bottom, ultimately to a stop command. Okay, and it will take them in order of how it gets it from the top to the bottom of the stack of commands. Okay, let's take a look at the next one. The next one says there are only 3 lines here. Okay. Again, we restart. The left hand is on 0 and the right hand is on 1. So we're going to shift the right hand to the right. The right hand is now on 2. And here is a jump command. So the jump to line 1 means we're just going to come back up to line 1 and start again. Do whatever it says in line 1 and try to make your way down to the bottom. So we'll shift the right hand to the right 1 position to 3. Jump back up to line 1. Shift the right hand to the right. Line 2, jump back up to 1. Right? I think we see that this is going to have, what should have, a very similar result to the last set of code. Except I hope that you kind of realize the problem here. Even when I get my right hand to 7, right? My right hand is now on 7. It now wants to jump back to line 1 and now move the right hand to the right again. Number 1, it's going to go off the end of the set of cards, and now my right hand is touching the desk, right? But the other problem is that the way this is set up is that this code is never going to stop. There is no way that this code gets to item number 3, the stop command. So this, in reality, this code would repeatedly, it would go over and over and over and never end. In programming, we call this term an infinite loop. This code will never stop. Well, it will stop if you force it to stop, or the computer would run out of memory. But in concept, the computer, this set of code would never end. This is called an infinite loop. This is a problem. All right, so this would really be an issue. This would be an error on the code. Okay. All right. So here we start to get a little bit fancier. Okay. So we now have, again, starting at 0 and 1, shift the right hand to the right. Right, so now the right hand will be on 5. Now, jump to line 1 if the right hand position is not equal to 7. Remember, there's a difference, the different commands you could have used. RHPOS, that's the right hand's position. We're talking about the number position it's in the list. If it said RH card, then we would be talking about the 5 itself. Okay, so two different options here. So we're going to go back to line 1. If the right-hand position, NE means not equal, is not equal to 7. Is the right-hand position 7? No, it's not. Go back to line 1 and move the card to the right. Is the jump to line 1 if the right-hand position is not equal to 7? Is it not equal to 7? Right now it's 3. That's not equal to 7. Go back to 1 and move the right-hand position to the right. Now we're on 4. Is the right-hand position not equal to 7? That's true. So go back up to line 1. Okay. I think you're going to see that this will continue to repeat itself. And now we're all the way at the end. Jump back to line 1 if the right-hand position is not equal to 7. All right, now that we're at 7, this will now be a false statement, and this will not jump, and then want to continue to line 3, therefore end in the program. Right, so hopefully maybe you remember this idea of if and a conditional statement. Hopefully you remember that from our work we did with spreadsheets. This is the same concept as an if function in Sheets and Excel, where we're doing something based on a condition. Right, so this will only jump to line 1 if this is true. Okay, so this will move the right hand until it gets to the end of the list. Right. Now, if I jump back here for a second, here you have 2 examples of code that does the exact same thing. Remember the first one, the first issue we looked at had 7 commands, and we kept repeating over and over and over, move to the right, move to the right, move to the right, move to the right. And now we come to this example where we can do the exact same thing in only 3 lines of code. Right? So we're going to come back to that in a second. Right? So this is really just a condensed, more efficient way of doing what we did in the first problem. Interesting. Okay, let's take a look at the next one. The next one says move the right hand to position number 7. Right, so right now, the right hand is sitting over here. Sorry for my drawing. All right, now shift the left hand to the right. When we say that, we're just going to move it 1 position. So the left hand, and I'm going to have to do this with L's and R's now. So the left hand is now sitting at position 1. Move the right hand to the left. So now the right hand is sitting at 6. Jump to line 2 if the right hand position is greater than the left hand position. Is the right hand position of 6 greater than 1? Yes, it is. So we're going to jump back up to line 2 and move the left hand again. So now the left hand is sitting at 2. And line 3 says shift the right hand to the left. So we're going to move the right hand back to 5. Is the right hand position greater than the left hand position? Is 5 greater than 2? Yes, it is. So we'll go back to line 2. Shift the left hand to 3. Shift the right hand to 4. Right, so that's lines 2 and 3. Jump to line 2 if the right hand position is greater than the left hand position. Is 4 greater than 3? Yes, it is. So now we're going to shift the left hand to the right. Right, so the left hand is now on 4. And we're going to move the right hand to the left, and the right hand is now on 3. Good. Is the right hand position greater than the left hand position? Is that true? No, it's not. The right hand is now less than the left hand. Therefore, we will not jump to line 2, and now we'll just end the program. Okay. So at the end, the right hand finishes at 3 and the left hand finishes at 4. Generally, this algorithm or this set of commands will stop the right hand. It stop the program when the right hand and the left hand cross each other. Basically, when it finds the middle of the list of cards, right, and the right and the left hands have changed and crossed over each other, and that's when the program would stop. All right. So something a little different here, a little bit more interesting. Okay. And this one just gets even a little bit more complicated. Right. So let's see. Again, we start back left on 0, right on 1. We're going to jump to line 5 if the left-hand card equals 9. Here's the first time we're using the card command here. Jump to line 5 if the left-hand card equals 9. Cool. Does the left-hand card equal 9? No, it does not. Okay. We're going to shift the left hand to the right. Right, so the left hand is now on 1. And move the right hand to the position of the left hand. Right, so wherever the left hand happens to be, that's where the right hand would want to move to. So the right hand is also on position 1. Okay, jump back to line 1. Jump to line 5 if the left-hand card equals 9. Does the left-hand card equal 9? Yes, it does. So that means we're going to jump all the way to 5. We're going to skip all of this and end the program. Boom, that was a quick, short one. So in reality, what's happening here is that the left and the right hand cards are going to just shift their way across the deck one spot at a time. And really what they're looking for is that these cards are looking for the 9, right? So we're going to go card by card and look for a 9. When it finds the 9, that's when the program would stop. In our example here, the 9 happened to be the second card, right? But if it was over here in position 5, the hands would slowly keep moving across the stack until it found the 9. Okay. But I have a question for you. If we were to think about this, what would happen if there is no 9 in the list? If we don't find a 9, could there be a problem here? And the answer is, yeah, there is no way to stop this program unless there is a 9 here. If there's no 9, these hands are going to want to keep going until China, right? This will not stop. So this could be a problem if it doesn't find a 9. We would probably have to add something in here. How would we stop this? We would have to find something that would involve when the left hand hits the 7th position. That would be a way to kind of stop the program, right? So this is one of the issues here. All right. So that was the solutions to some of your problems here. The goal here was to just kind of get you used to the flow of programming languages, right? How do these elements work? Getting it maybe into the mindset of working top down and following the flow of commands. Okay. And then getting also used to working within a limited set of commands. The only commands you had to use were the ones that were on that reference sheet there, where we had shift and move and jump to line if and jump to line and stop. So we have a limited set of commands that really you could do almost anything with. So we're getting used to doing that. And we're going to play a lot more in the next 2 weeks about working with commands like this and really starting to learn coding. Okay. So we're going to jump to another slide here, maybe to wrap up here. So some thoughts here just to kind of end this little section here. Computer science is a very technical, it's a technical discipline, but it's also a very creative discipline. First, different algorithms can be developed to solve the same problem. It is possible that we can both approach a problem in a different way. We could all take different strategies. I believe when we did the peanut butter and jelly sandwich algorithm, a lot of us had slightly different, differing algorithms. When you wrote the find the smallest card algorithm, some of you approached it from different ways. But there's nothing wrong with that. We could argue about whose algorithm is the best. Quote, what is your determination of best? Is the best algorithm one that uses the least number of lines of code? Is there one that maybe is more efficient than another? Sometimes we look at coding algorithms, who's the most efficient as far as like computer usage, like how much CPU power does it take to run this command, how much RAM does it take, how much hard drive space does it use, right? So they're all different ways to figure out which one is the best one. But kind of the neat thing about this is that there can be a couple of different ways to approach a problem, right? And they're all valid. And then even when we agree on an algorithm, different code can be written to implement the same algorithm. We saw it here just in this example. We had two different ways to get the right hand to the end of the list, to card number 7, right? So we had one algorithm or one set of code that took 7 lines of code in order to do that, and we had one that took only 3. But they both work. And we could argue later on about, again, what is efficient, what is best, what is the correct way of doing this. But there is a lot of room for creativity. There's a lot of room for differing opinions. And there's a lot of room for personal preference when it comes to working on a problem, figuring out a strategy, and then writing code to implement that algorithm. So we're going to see that going forward as we now start to play a little bit with coding. That we could all approach problems in different ways, which is totally okay. And we can both approach the same strategy using slightly different code. And that's really okay too. So if you're into problem solving, if you're into like solving puzzles, computer science could be a really interesting area of study for you. Right? Where it's all about, I have to be able to solve this problem. And what are the different ways that we can come up with it? What makes the most sense? What's the most logical? What's the most efficient?